Okay. Sounds vaguely ominous, doesn't it? Anyway, hi, I'm Joe Paisley. I'm work with the Pikes Peak Library District and this program, Skype a Scientist, which of course is actually on Zoom, as you well know. But alliteration is one of our vices here at the library. So we went with Skype a Scientist, obviously. But this is part of our winter adult reading program that's ongoing through the end of March. Hope you guys have the opportunity, please sign up. We're actually doing really well. We're on our way to setting a record for participation and as important as just as important completions as well. So people are, I think, taking advantage of this. So that's great. But today we'll welcome Christopher Jones. He's a PhD student at the University of California, Riverside, studying, and here's some big words, so brace yourself, geobiology, marine geochemistry, and marine biology. And I first off have to admit, I don't entirely understand what that means, but Chris is going to explain that to us as part of this. But basically, to sum it up, he studies modern oceans and its processes to better understand how the Earth has changed through time. So without further ado, let me hand it over to Chris here. Thank you so much. I have just go ahead.
Thank you. Let me share my screen. Can you see this? Yeah, okay. So yeah, I thank you for having me. I really love this program because it allows scientists like me both to practice our presentation skills and to like meet people across the country. And this is my, I had always done it for like elementary schools before. And so it's really cool to get to do it for an adult reading program, which is nice and enjoyable. So yeah, this is just like a little bit more about who I am and sort of what it means to be a marine geologist and marine geochemist. So these are some pictures of me on a research vessel that I went on called the Polarstern. It's a German icebreaker. So we were in like the South Sandwich Islands in South Georgia, which are like these islands down near Antarctica. And this is like what daily life looks like on the ships. Like, this is me getting off the ship. So you can see like how big it is. We all lived on there for 2 months straight. This one on the top right is me sampling a core. So we were taking sediments from the bottom of the ocean. I then went back to my lab and I dissolved the sediments with like all these acids and chemicals and things in our lab. I went to Oklahoma State University for my undergrad. So did that there. This is what the scenery looks like. So it's a pretty cool place to be. There's always great people and great food as well. So this is just sort of what it looks like and how it is to be a marine geologist. Another thing that came up last time I did this a couple of weeks ago was, why Colorado and why oceans? So I just thought I'd throw this in here to sort of show that the Earth has really changed through time. So this is looking at this bottom right is a map of what North America could have looked like millions of years ago. And of course, on the left, you can see North America today, where you have the Laramide orogeny, which is one of the ones that's brought up the Rockies. And so that's why you have all these mountains in the plateau and everything. And so obviously there aren't oceans there, but used to sea level was higher and those mountains had not yet risen. So parts of Colorado were actually underwater here. So you used to be actually right on the ocean. So if you went back millions and millions of years ago, you'd be underwater right now. So understanding how the ocean works is really pertinent to understanding the development of lots of different areas across the Earth through time. So this is going to be like a sort of hodgepodge of how the ocean works, its layers, and then also how we study the ocean. I took some videos when I was on these ships, and so I've taken some snippets that we'll get to watch as well. But the first thing is just to understand ocean currents and how they circulate, which is one of the big drivers of heat transport across the planet. So you can see all these arrows, right? These are mainly driven by wind currents and atmospheric circulation. And the red ones are the warm currents and the purplish blue ones are the cool currents. And so it makes sense, right? So you have along the equator, you have this lots and lots of sunlight basically that heats up the air, and then the air flows and it sort of just drags the water along with it. So then you get these warm currents, and then eventually they hit the continents, right? So water can't flow all the way over or through the land mass. And so it sort of bends either north or to the south, and it forms these gyres. So it's just the circular thing, because eventually they hit another continent and they sort of just go around in circles over and over and over again. As they flow further to the north, they start to cool down, and they mix with cold water coming from either the North Pole or the South Pole. So then you get these cooler currents that flow back down towards the south, and they heat up again, and you repeat the process over and over again. It takes, I think it's like order of like maybe decades or so for water to make it all the way around in these surface currents. And you can track this using things like there's like in the middle of the North Atlantic, there's this, not like an island, but it's a floating pool of sargassum, which is like I think it's an algae of some sort. And it just like floats around. You can track its movement through like satellite imagery and stuff like that to see how this flow is going. Another fun fact is that, so this warm water coming up from like the Bahamas and the Caribbean, it's the reason why like the Northeast and also Northern Europe is still pretty habitable, because otherwise it'd be pretty far north and be really cold. But you can find palm trees actually up here that survive based on the heat transport coming up from the equator through these ocean currents. It's all wind-driven circulation, so wind just basically has a frictional drag. That's what you see, like if you were to go to the beach, you would see, you could feel the wind coming off the ocean. You can also see the waves coming at you. That's the main driver of those. And this is a video clip. I hope that it works. And it's just showing, it'll just show sort of like what life is like getting onto the ship and sort of why we were doing the things that we did.
And then we'll do that. So we're just about to leave on the research vessel, the Polarstern, which is an 118-meter research ship. And we're about to head out to the South Sandwich Islands for 8 solid weeks.
The deep ocean is part of our Earth. And if we want to understand our Earth, we also have to know the deep ocean. Specifically, Antarctica is an area which is not very well known. And therefore, we are trying to design expeditions to explore this area.
The half crab is a fist-sized white crab that lives on the black smoking hydrothermal vents in the Antarctic. What we want to find out on this expedition is more about the life of the half crab, where it lives, and how they live and interact together.
So we're about halfway on our voyage to South Georgia, and the wind has just started to pick up. And we have a meteorologist on board, and he says in the next 48 hours there's a storm coming, and he thinks there's going to be 5-meter waves. So the next couple of days could be quite rough.
We have wind speed 8.4 now, and the wave heights are 6 meters around. The swell also here around 4 meters from southwesterly direction. Yes, that's quite hard.
So I hope what you got from this first part of the video, there's like 2 more that I'll show clips of, is that there are lots of different people on board, right? So I'm a geologist, but oceanography and studying the oceans in general is not just about the rocks, right? There were people that were looking at those Hoff crabs. So there were biologists on board. There was a meteorologist. There were people who were studying like penguin populations and fin whales, and people studying wind patterns. There were volcanologists on board because one of the islands we went to was a volcano. So there's lots and lots of different people. And then even on top of that, there were the people that were actually on the ship, like they're running the ship, and engineers and sailors and all these things. So studying the oceans is a really interdisciplinary field, and lots of different types of interests, and people with different interests can be on board. So this is just showing one more thing about how we have tracked ocean circulation through time. So this on the left is showing the wind patterns. And so we have things like the trade winds, which if you've ever seen like Pirates of the Caribbean or something, they talk about trade winds and westerlies. So this is just showing how they circulate. And then these gyres mimic those circulation patterns. And there was an accident in 1992 when a shipping, like a large shipping vessel, I think they like went into a storm, and a shipping container that was, I think it had something like 30,000 yellow rubber duckies in it, fell off. And then of course it broke, and then the ducks were released into the ocean. And because of that, they knew like by the serial number when each one was created and like which batch they were from. So they were able to track, people would like go to the beach and they would find them all across the world, right? And they could see, oh, this one landed in this one. So here in Sitka, there was one that landed in 1994, 1998, 2001, 2003, one in Hawaii, all over the place. Based on the year that they made landfall, they could see how long it had taken the water to make it from this accident here in the Northern Pacific all the way around the world, up to Maine in 2003, to Scotland also in 2003, over and over and over again. But even in some places like here in Sitka, a decade later, you had another landfall, even though ones had fallen and washed up on shore even earlier. So it shows that sometimes the ocean goes all the way, like water will go all the way around the ocean, but sometimes it gets trapped in these little tiny gyres, like this subpolar gyre. I just think it's really interesting that an accident involving yellow rubber duckies is what helped us understand ocean circulation much better. But something to consider is that this is only talking about the surface ocean, right? So the ocean is really, really deep. I think the deepest point is just over 36,100 feet, which is taller than the highest mountain. So height of Mount Everest, even though I think Mauna Kea, one of the Hawaiian islands and volcanoes, is actually from base to top taller, just not above sea level. So the ocean is the deepest, that has the deepest place in the world, and it has all these different zones. So this figure on the left is showing the different zones. So the epipelagic zone, which is the sunlight zone, so that's where sunlight can reach down and penetrate. So you can have things like photosynthesis and algae and stuff growing there. That's where like most like fish and all the things that we think about like to live, because that's where there's a lot of food and nutrients and things. Below that, you have the twilight zone, where it's starting to get dark. There might be a little bit of sunlight depending on different conditions, but most of the time it's pretty dark. Then you have the bathypelagic zone, which is also the midnight zone, which is where you have total darkness all the time, but it's not super, super deep yet. It's only maybe to 4,000 meters or so. You have the abyssopelagic zone, which is on the abyssal plain, which is like this, like when you think of the ocean, you have the continental shelf, which is like when you think of like a beach, that's where it's like sort of shallow-ish. And then you have the continental slope, which is where it goes down to the abyssal plain, which is a pretty flat. Most of the ocean is the abyssal plain, where it's sort of flat and stable. And then you have trenches and things like that as well. So the abyssopelagic zone is where that is. This is also where the Titanic sinks or sank, and where it's resting now. It's resting on the abyssal plain. And then you have the Hadal zone. So Hadal coming from Hades, the Greek god of the underworld. And it's where you have trenches and things like that, and subduction zones. And that's where you have the really, really, really deep areas. Even though they're so deep, we've actually been to the bottom. So James Cameron went to the bottom of Challenger Deep, which is the name of the deepest part of the Marianas Trench. And so we've been down there. And what's surprising, that we still found life. So this figure on the right is showing the different layers of the ocean and the type of organisms that live in each one. So like I said, the top is where we think of a lot of things like whales and dolphins and turtles, jellyfish, lots of fish. all those sorts of things. And then as you go down and down and down, deeper and deeper, you start to have a little bit less life, but they're still present, right? So things like squids can live really, really deep down, and tube worms and sea cucumbers and starfish, they live down at the very bottom of the ocean as well, although you could find sea stars also on beaches. So they're really, really diverse. But when they got down there, they'd sort of expected it to be sort of empty and just this like, empty wasteland almost, but they found life all over the place, which I think is really cool and goes to show that we don't really understand the ocean system super well. We actually sometimes, it's a pretty commonly quoted thing that like we know more about the surface of the moon and the surface of Mars than we know about the bottom of our own ocean. So that's why we want to go study it. So looking at that deep ocean water, so all of these layers also often have ocean currents within them as well that are different than the surface ocean currents. So the thing that drives that in the deep ocean circulation is the density, which is controlled by temperature and salinity. So on the left, you can see it's called the thermocline. And so this red line just tracks the temperature basically of ocean layers. So at the very top where there's sunlight and all these things, it's actually pretty warm. So this is in Celsius, but like 22 Celsius is pretty, I'd estimate it's maybe like 70-ish degrees or so Fahrenheit, between 60 and 70. And so it's like nice and temperate and happy to live. As you go deep down, you go from this warm area where it's well mixed because of those surface currents to this really, really cold, almost freezing bottom at the or temperature at the bottom of the ocean. Salinity tracks that. So salinity's high at the very surface, and then it has a decrease and it comes back up. And then the same for the pycnocline. Pycnocline is just the word for density. So density is low at the surface because it's high temperature, and then it's greater at the bottom of the ocean because of its low temperature and medium to high salinity as well. So this is just showing sea surface density globally. And the reason I'm showing this is because you can see that the highest density is at the poles, right? So there's high density here around Greenland and like north of Norway and Northern Europe. There's also this red area around Antarctica. So what happens is because the water is dense there, it actually starts to sink. This is partially related to sea ice formation. So during the winter, when sea ice expands, you are making the water denser because you're taking fresh water out, leaving salt and things behind. So it gets denser and it starts to sink. And then what happens following that is you can track the sinking of that water. So looking at like this like purple layer, the sinking of that water comes down and flows across the bottom of the earth or the bottom of the ocean. So that's these are these different Antarctic, like this is the Antarctic bottom water. This blue one is the North Atlantic deep water, and they flow, and based on their different densities and temperatures and things like that, they flow either over or underneath each other, and they cause this long-term transport of water from the poles down across the earth. This is tracked in some ways by looking at the age of the water. So radiocarbon is, if you've ever heard of like carbon dating or something like that, that's what this is referring to. And it's just based on the decay of carbon isotopes and how basically their ratio to each other is showing you how long the system has been in place. So then you have, you could track the formation of this North Atlantic deep water, and you could measure it all the way along these black lines and black squiggles showing its circulation. And then based on that, you can look at its age and see how long it's been traveling. So you can see that some of the water is thousands upon thousands of years old, depending on how far away it is from its point of formation. I think the total time for like ocean overturning circulation is maybe on the order of a few thousand years, depending on different continents and where the continents are and all these things as well. Also depending on sea ice formation and how strong it is. this is just showing what's often called the global overturning circulation or thermohaline circulation, sometimes also called the Great Ocean Conveyor Belt, because it's just showing how you form this cold, deep water and it flows across the entire ocean floor. And then eventually once it hits like a continent or something and it can't go anywhere else, it upwells, comes back up, brings this like nutrient-rich deep water up, leads to a lot of like productivity. So algae and fish and things can grow, and it heats up and then it flows back across the Earth's surface through like surface ocean currents and things like that, makes it back up here and then gets cold again, sinks, so on and so forth, over and over and over again. Okay, so this is one of the ways that we study that. So this first device is called a CTD, and it stands for conductivity, temperature, and density measurement. So the conductivity is for the salinity, so how much salt there is, temperature, and then density. So we use this device to track that, and then this video will also show a couple other devices too.
Lights up. The special thing about this ROV is that you have
an ROV is a robotically operated vehicle. So he's going to talk about the ROV that we used to study the ocean floor.
You have your hands and your eyes at the seafloor down to 4,000 meter depth, which gives you insight into a universe which is inaccessible for human beings otherwise.
This is just it being deployed, just showing sort of what it looks like and how we do it over the back of the ship.
We land on the floor. Okay, this is the suit. The suit is in the middle, yeah.
Wir sind also, wir sehen also schon, ach so, okay, ja, das kannst du dann noch nicht erkennen. Ja, tut mir leid, also wir warten dann, bis es eingeschaltet werden kann.
These are some black smokers we found.
You are speechless.
And then penguins, of course. So one of the cool things about penguins is that they actually use icebergs as sort of floating islands. So they'll like jump up on them and rest for a while before they go back out and swim again a little bit more. So this is the last video, and it's just showing more of what I did and what marine geologists use. So it's a coring device called a gravity core. So it sort of acts like a straw. So you lower the straw down all the way to the ocean floor, and it sort of sinks down a little bit into the sediment or the rock. And then it has this catching device at the bottom so that whenever you pull it back up, all the stuff stays in it. So this is just showing how we deploy it. It's a fast motion, so I don't think it has sound for most of it. But this is just like, there's an engineer here, and in mechanics and everything, they're making sure it's all set up properly. Then it goes over the side, they do some final checks, and then that wire is what lowers it down. And this is bringing it back up, which is the hardest part, because you have to make sure it lines up properly with its little cage. and it weighs a lot. I think there's 1 ton of weights on the top, so 2,000 pounds. And this is what we do afterwards. We extract first we like suck off the water from the top of the core, and then we go forward and we slice the sediment, and then we analyze the sediment afterwards. So that's all about oceans on the Earth, but we're not the only place actually, even in our solar system, that have oceans and water. And so these are 2 pictures that from NASA showing what Europa, which is one of the moons of Jupiter, so Jupiter, the planet here in the back right, looks like. So you can see that there's this geyser of water coming out, but most of the surface is covered in ice, right? Because it's really, really cold out there, farther out in the solar system. So the surface is ice, but you can see all these cracks, and those cracks vent out water and gases and things like that. And so they're really curious about studying the inside and looking at the water world, like the ocean, the layer of the ocean that exists underneath the ice. So this is a model of what another icy moon, Enceladus, which is one of Saturn's moons, might look like. So you can see the ice crust on the outside, some geysers coming out at the bottom. And then there's probably like a rocky core similar to like what our moon looks like on the inside. And then between the rocky core and the outside ice layer is this liquid ocean in between. And so I think there's actually, so that NASA is planning some missions to go study these. This is one of the reasons why one of the big questions is, are we alone in the universe, right? And so they think that these ocean icy moons with oceans underneath could be places that have other like extraterrestrial life on them. They don't think it's probably not going to be like little green men on Mars or anything, probably just like microbes if they are there. But this is a model for how they think it could happen. So you have this rocky core and then hydrothermal activity, which things like black smokers and vents and stuff where there's just like heat from the inner rocky core, sort of the same way that the inside of the Earth is really hot, gives that energy basically for life to start, and also provides this cycling of nutrients and things coming from out from the rocky core. And then they might live in this ocean world beneath the outer ice core above this rocky core where there's these vents, and then we could go through and fly through this plume, like the geyser almost, and try to measure what's in the water that's coming out and to see if we actually can see any signals for life. So that's one of the reasons that we're really interested in ocean worlds beyond. But if you've ever watched like a science fiction movie, this picture on the left is from the movie Interstellar, which I think is a really interesting like thought experiment. Would ocean worlds actually be able to support life like us? So life like humans. And so the question is, it really depends. Some people say yes, some people say no. Science fiction has had its say in many ways. This is the picture, and it shows this huge wave. Based on just like gravity and circulation and stuff like that, they were thinking that, okay, you know, if we had an ocean world with no continents, there'd be nothing to ever stop a wave from forming. And so it would just build up over and over time. And then you get this massive one that just circles the planet out at all times. If you've ever seen the movie like Poseidon, you know about rogue waves and how they're kind of scary. So maybe they wouldn't be able to support life like us, but the question is still out there. So that's the end of my presentation. I did have one thing that I forgot about to put in. I remembered it right at the beginning is, if you've watched the news recently, there was Ernest Shackleton, who was an early like explorer of Antarctica. His and like oceanographer, his boat was just found. It had sunk in the ice. It's called the Endurance. So if you want to Google that, I definitely recommend reading about it because it's a cool history lesson. He the ship got locked in the ice and then they abandoned it. And I think he and like 6 crew members maybe took like a rowboat or like a little lifeboat, and they rescued everyone. So everybody survived. even though they were marooned in Antarctica. But the Endurance was just found this last week, I think, at the bottom of the ocean. So that was the one last thing. Otherwise, I'm happy to take questions and comments.
Okay, well, Chris, thanks very much for that. I appreciate it. I had a question for you. You mentioned you went to Oklahoma State. I think if I recall correctly from our first session, you're from Oklahoma originally. I was wondering if you could share how a kid from Oklahoma ends up doing what you do, since you're not, oceans are not what come to mind when Oklahoma comes to mind.
Yeah. So I always wanted to be a geologist. My grandparents on my mom's side lived in eastern Oklahoma, which has like lakes and rivers and the Ozarks and stuff like that. And there were some fossil collecting sites near their house. So my grandfather would take me out all the time to go collect fossils and rocks. So that was how I really first got into geology. The way that I got into marine geology is I was also really interested in biology when I was in high school. And so I wanted to study like microbiology and how it interacts with like the Earth system. And one of the best ways and one of the areas that it does it the most is in the ocean system. So when I went to college, I was like, hey, this professor in the geology department was studying sort of that topic. And I asked her if I could work in her lab, and she said yes. And here I am doing my PhD in that now. So.
Great, thanks. Yeah, if anyone has a question, you're welcome to unmute yourself and ask, or you can go ahead and type it into the chat and I'll see it and say it to, Chris will either see it or I'll repeat it for him. So we do that, but I'll go ahead and throw a couple more questions. I got a few more questions here that I set aside here, but I guess the big question is, why should we study the oceans and marine geology? You touched on that a little bit, I think, when you were talking about what's interested, but could you sort of explain to us why? Well, here's a good example. I got a Facebook comment when I promoted this thing. Someone said, well, Colorado is really far away from the oceans. How is this relevant? Please explain to me, and hopefully someday that person, hopefully if they watch this, why it's so relevant to us here in Colorado.
Yeah, so like I showed at the beginning, if it will go back is the question. So Colorado is not under the ocean now, but it used to be, right? So a lot of the rocks that you'll find, especially along the Front Range, there's shales and things like that, which were deposited under a deep ocean, right? And so understanding, the history of even just Colorado and just the history of the Earth in general is really important, especially because the ocean covers over 70% of our surface, right? So it's the majority of our planet is actually the ocean. So some people even argue that we ourselves are on an ocean world. We just have like some isolated land continents, right? It also is the main controller of things like climate. So and weather patterns, circulation of precipitation and stuff like that. It's one of our largest sources of food in the world. So if you've ever had seafood, then you have to be getting it from the ocean originally, or like a farm along an ocean. It moderates things like carbon dioxide in the atmosphere, so CO2 can dissolve into the ocean, and so that's why it's not as high as it could be right now. On the flip side, that acidifies the ocean, which is not good for the animals that live in it. So it's super important for moderating our climate and providing food and all these sorts of things.
We have a question for you.
Mm-hmm.
I have a 14-year-old enthusiast here. So he has a question.
Yeah, of course.
What kinds of things would you look for in core samples to indicate a new layer of strata?
Very good question. So it depends on where you are in the world, because there are different types of like sediments and organisms. one of the ways that people do it is using paleontology, so the study of like organisms and fossils, right? So once you find a new organism in a layer, you can know that you're in a different layer now, right? So looking at the succession, it's called fossil succession, is one of the ways. Sometimes people use like ash layers. So say there's a volcano nearby, if it erupts, it'll leave a layer of ash that you can then identify, and that shows a new layer. If you are interested in dinosaurs at all, the meteor that hit the Earth 65 million years ago, when it hit the Earth, it ejected all this stuff up into the atmosphere, right? Like rocks and debris and ash and all these things. So you can look at that layer. It's actually, they first found it in Italy. They didn't even find it in the Yucatan Peninsula. So they found it all the way in Italy, and they're like, huh, this looks kind of weird. It shouldn't be here. So they identified it that way. Some people look at chemistry. So like I said, I'm a marine geochemist. So I look at changes in like which elements like iron and nickel and stuff are in there. That can tell you different layers. Sometimes it's just super clear. You can see like it goes from brown to black and you're like, oh, wow, that's really obvious. So yeah, there's lots of different ways.
Yeah, it looks like Natalie had a couple questions for you. Let's see. What types of industries are using the information you were able to learn, and how are they using that information?
Okay, yeah. So one of the biggest industries is probably like the energy industry and like oil, because looking at like how oil is deposited or formed, you have to have a lot of organic matter. So think of like a lot of algae or something like that that grow and then they sink and then they're buried in the sediment. So they want to know when oceans were really productive and had lots of life, and then also when they could have preserved a lot of that. And so the research that like I work on can tell you about oceanic conditions in the past. So they want to know about that. People doing mining, so like the mining industry, there are people who want to like mine parts of the ocean seafloor for things like lithium for batteries. So they use geologists for that, but also lots of people like studying like atmospheric and oceanic interaction and weather patterns. They want to know how the ocean is circulating and what might change ocean circulation. So they use people at like the National Weather Service or other like weather related programs will use that. Government agencies use lots and lots of geologists and oceanographers in general to study those things as well. Think about like hurricanes and hurricane patterns, all of that. So yeah, lots of people.
Chris, I had a question. I'm looking at your screen here and it shows, obviously the ocean, part of the North America, a lot of North America being covered by the ocean.
Mm-hmm.
It seems across I see it down here and I'm circling around Texas. Did that have any, with the ocean there and the algae you're talking about, did that have a connection to oil production? Because Texas is well known for having a lot of oil. Is that connected? Am I understanding it correctly?
Yes, yeah, exactly. So North America has been submerged multiple times, but this one specifically I chose because like Midland, Texas, where like there's a lot of oil right now, all of that was forming when Texas was underwater under this period. And so it's on this, what we would call a Western Interior Seaway. So the western part of the continent, it's in the interior. It's the seaway because it connected this part of the ocean and that part of the ocean. Was a time when there was a lot of like there were lots of nutrients and it was also sort of restricted, so everything was trapped, and so they all just settled out right there in that basin. So yeah, this is exactly how all that oil formed.
Thank you. Natalie had another question here. She's wondering, how long is your longest experiment and what data are you finding out from that experiment?
So my personal longest running experiment is it's going on about 3 years. And so I had like a time point at like 4 months, 8 months, 12 months, 1 year, and then like I'm a year after that or 2 years after that now. And what I'm studying is, so I like took some sediment, think of like sand and silt and stuff from the bottom of the ocean. And I like put it in this tube, and then I sealed it and just like cut it off from like any interaction with like oxygen in the atmosphere, and like no nutrients are being put into it or anything. It's just like sitting there. And I wanted to see what are the natural processes that will occur in that sediment, mostly driven by like microorganisms that were already living in the sediment. So what I've found from it so far is that they cause a release of metals, like iron, for example, is released from like the actual sediment grains. They dissolve and release their iron into the pore water, which is like all the water between the grains. And then some of the metals, like on top of iron, there's one called like molybdenum, is released as well, and it actually is released in such high amounts that it might become toxic. And then it's caused a shift in which microbes are actually able to live at the time. So, but it's still ongoing, so it's not an actual like perfect finding yet. But so far, that's what I've found so far.
Thanks. And one more question from Natalie. She wonders, she's asking who funds most of your work and why?
Yeah. So funding for this comes from a lot of different places. When I was in my undergrad, I got like some university grants, like university undergraduate research grants, that were often from like donations from past alumni or something. They like created a foundation in their name to promote undergraduate research. So that's where I got most of that funding. The funding that I have now is through my PI, so my advisor at UCR, has a lot of funding through NASA, because he is looking at like, we're thinking about like, how to study the Earth and how it's supported life through all these billions of years, and how we can think about other planets in the universe and how they might support life similarly. So we have a lot of funding from NASA. Other ones like the National Science Foundation, the National Institutes of Health, United States Geological Survey, the Geological Society of America as well. I got like a grant from them. So it's lots of different organizations. Oftentimes they're government organizations, but sometimes like industry will also fund. So like ExxonMobil has grants that they'll give out as well. And then the why is it's a big question. I mean, oftentimes it's because we have like relevance to understanding our climate or how Earth's climate is working or how it's worked in the past. But there are lots of different reasons for why. So.
Okay, we're let's see, it's about we're getting close to the end here. So if anyone else has any questions, please speak up or type in the chat. But I'm going to go ahead and got another question for you, Chris. Sort of wondering how could the oceans, I mean, obviously the oceans have changed quite a bit over time. I'm wondering how they could change now and in the future, and how humans might be affecting that process.
Yeah. So now and in the future, we'll probably continue to see a little bit of sea level rise, which parts of sea level rise are natural. Other parts are driven by like melting of ice, like glaciers and continental glaciers and things. And part of that is being driven by, like greenhouse gas emissions from burning fossil fuels. And so like sea level rise, but also like I talked about, if you change the temperature and like make the poles warmer, you won't form as much of that deep water. So you'll like weaken ocean overturning circulation and all that stuff, and weaken just like circulation in general. And that's important because that's one of the main drivers of like recycling nutrients within the Earth system. So when you think about fisheries and things like that and food sources, if you affect all that circulation, you're not going to be able to have as much productive life in the ocean. So that'll affect like, how much fish we can grow and algae and all that sort of stuff. Another part is like, if you've seen like the ocean acidification and like the whiting events in the Great Barrier Reef, where like the corals cast off all the little algae that grow with them or whatever, and suddenly they're white and they don't have all the color anymore. So that'll affect coral reefs and things, which are the most biodiverse places on our planet. And so that would be also another consequence of human actions.
Okay, it looks like, yeah, we got one more question here. It looks like I got time for one more question. It seems like a good one to end on, but when you're not feeling like being productive in your research and you want to break, what do you do?
Oh, that's a good question. So I'd say like oftentimes the way that I get around that is I have multiple sort of projects going all at once, right? So I'm not working on just one thing at any given time. So if I get sort of bored, or not necessarily bored, like confused, or like I'm at like a point where I'm like, I don't really understand what's going on, I need to like think about it for a while. I just like sort of shift and work on a different thing. I also, so like as a PhD student, some quarters I have to teach classes as well. And so when I'm teaching, I don't do as much research at that moment. And so like, that's like a sort of break in the research. Other times I just like take a day off, and, you know, sometimes you just have to have that time just like for yourself. So sometimes it happens. My advisor is very nice, and he says we should definitely take vacations during the year. So sometimes I take a vacation and like go away for the weekend. I really enjoy rock climbing. So I often do that when I'm have like a mental block. So
Yeah, definitely something landlocked, if anything else, to get your mind off the oceans for a little bit. Yes,
yeah,
I hear you.
yeah,
Yeah, I hear you.
most definitely.
Well, thank you for giving us, first off, thanks for being so generous with your time doing this for us. We really appreciate it. I know I learned a lot last time, and I've learned even more. And I hope the class that's watching this recording is going to learn a lot too as well. So I think so. Thank you so much for your time. I appreciate it. Thanks again. Thanks to everyone for joining us. I appreciate it, especially, and thanks for making time for us here. Again, thanks again. Thanks to everyone. I'm going to go ahead and stop the recording. And if it'll let me, there we go. Stopping recording now.